Okay, so let's take a look at past question review on material science. So this is actually a question from 2017, question 2 precisely, 2017, 2018 past question material science in River State University, Port Harcourt, Nigeria. So the question says, molybdenum is a BCC metal with atomic mass 95.94 and lattice constant 3.147 Armstrong units. Determine 1. The density of molybdenum. 2. The number of atoms in each unit cell of molybdenum. 3. Determine the distance between two nearest atoms of molybdenum. And then the question continues, it says, is it possible to have an element with the quantum number n equal to 3, I equal to 1, mx equals minus 1, and ml equals 0? Give reasons for your answer. Finally, the question still continues and it says, list the possible quantum numbers when the principal quantum number n is equal to 4. Alright, so let's start with the first part of the question. First part of the question says, molybdenum is a BCC metal with atomic mass of 95.94. So we'll get down our parameters. We are given atomic mass to be equal to, that's capital M is 95.94, okay, that's grams, and with a lattice constant parameter, so we're given lattice constant, okay, we're given lattice constant A to be equal to 3.147 Armstrong units. Alright, so the first question is asking us to find the density of molybdenum, and I think I'll start with the second question because we'll need what we'll get in the second question to actually answer the first question. Second question says, determine the number of atoms in each unit cell of molybdenum. So we have to find the number of atoms. First of all, we are given crystallographic structure. The structure is a BCC, a body-centered cubic structure. Now let's start with the second question. We have to find the number of atoms that makes up each of the unit cell in molybdenum. Now we are told that molybdenum is a BCC structure. And what is the body center cubic structure? Let's draw our simple cube to denote that. So we have our body center cubic structure. Okay, this is our simple cubic structure first. Now on each corners of the cube we have corner atoms. So there are corner atoms here. There are corner atoms here. On each corner of the cube we have corner atoms. We have corner atoms. We have corner atoms, and we have corner atoms. Now the total number of corner atoms here appears to be 1, 2, 3, 4, 5, 6, 7, 8. So we have total of 8 corner atoms. But as we all know, it doesn't actually mean 8 corner atoms. Each of these corner atoms are actually contributing 1/8 of their volume. So this is contributing 1/8 of its volume. This is contributing 1/8 of its volume. Same thing as this. So each of the corner atoms are contributing 1/8 of their volume. So this is now the simple cubic structure. Now, but we were told that molybdenum is a body center cubic structure, and for body center cubic structure, we have a central atom, an atom at the body of the cube. So it's just like having a mental picture of 8 atoms resting on one atom. So something like this, we have one central atoms, and then we have 8 atoms resting on this particular central atom. So you have to now picture the remaining 4 behind. Okay, you have to picture the remaining 4 of these atoms now behind. So these 8 atoms are actually resting on what? The central atom. And we know that each of these 8 atoms are contributing 1/8 of their corner atoms. Therefore, the second question says find the number of atoms in each unit cell of molybdenum. Hence, number of atoms is now equal to, so since we have 8 corner atoms and each of them are contributing 1/8, you have 1/8 times 8 corner atoms, okay, plus the central atom is contributing its entire volume, so it has 1. So this is actually equal to 1/8 times 8 will give us 1 plus 1, which is equal to 2. So which means the number of atoms for molybdenum, since it's a BCC structure, is actually what? 2 atoms. Alright, so that's the second question. The first question is saying we should find the density. Okay, we have to find the density D, and density is given as N times M all over Avogadro's number. Okay, Avogadro's number times volume of the atoms involved. Now, to get N now represent the number of atoms for the molybdenum, which we found here as 2. M represents the mass number or atomic mass, which was given to us earlier in the question as 95.94. So we need to now find the volume. We are given lattice parameter. Okay, recall we are given A to be equal to 3.147 Armstrong units. So you do well to convert this to, okay, it depends on your conversion technique in wherever you're watching from. But in Rivers State University, you always convert to centimeter because the lecturers usually make use of their conversion in centimeter. So which means you have to multiply this by this 3.147 multiplied by 10 to the power of minus 8 in centimeter. Okay, so centimeter is preferred in Rivers State University. Now we need to find the volume. Okay, to obtain this volume now, volume V is simply what? A to the power of 3. Okay, because this is actually spacing, distance between two atoms. The distance between two atoms is called lattice parameter, and is measured in centimeter. So to get the volume, since this is a cube, since the structure is a cube, it means the volume becomes the volume of a cube, which is distance to the power of 3. So this is now equal to A was given as 3.147 by 10 to the power of minus 8 all to the power of 3. So this gives us the volume. So let's obtain that multiple. 3.147 exponential minus 8 to the power of 3. That gives us 3.10 by 10 to the power of minus 23. So we have 3.10 by 10 to the power of minus 23 in centimeter. Okay, so we have to now plug in these values into the formula for density. And if you do that, you have this to be equal to density now becomes, remember, N represents number of atoms, and we've obtained number of atoms for molybdenum to be equal to 2 since it's a BCC structure. So you have 2 multiplied by M, there represents the atomic mass, and it was given in the question as 95.94 all over. Now VAV here represents Avogadro's number, and we know that Avogadro's number is a constant value given as 6.02 multiplied by 10 to the power of 24, okay, times the volume which we've obtained now times V, and V is volume, and volume here is 3.10 by 10 to the power of minus 23. Okay, all right. Okay, so please take notes. Avogadro's number is actually to the power of 23 and not 20 and not 24. So we have 6.02 by 10 to the power of 23 for Avogadro's number. Okay, so just make that correction. Pardon me for that error. So you have this. All right, so we obtain this multiple now. First of all, find 2 times 95.94. This will give us D to be equal to, obtain 2 times 95.94. That gives us 191.88. So we have 191.88 divided by, next we obtain now 6.02 by 10 to the power of 23 multiplies 3.10 by 10 to the power of minus 23. So that gives us approximately 18.662. So we have 18.662. So this simply implies that density is now equal to 191.88 divided by the answer. Okay, so our density is simply giving us 102.82. We have 102.82 grams per centimeter cube. That becomes the density of molybdenum. Okay. The third question says determine the distance between two nearest atoms of molybdenum. So to find distance between two nearest atoms, okay, distance D is given as A root 3. Distance between two atoms is given as A root 3, where A stands for the lattice constant, and this is equal to lattice constant was given as 3.147 by 10 to the power of minus 8 multiplied by root 3. So we have distance to be equal to 3.147 by 10 to the power of minus 8 multiplies root 3. So let's obtain root 3. Or let's just, okay, root 3. Root 3 gives us 1.7321. You have 1.7321 approximately. So multiply this to the Armstrong units. Multiply by 3.147. You have 5.45. You have 5.45 by 10 to the power of minus 18 centimeters. So you can actually say distance between atoms is equal to 5.45 Armstrong units. That becomes distance between two nearest atoms. Okay, so that's the first part of question 2 answered. Alright, so let's look at the second part of that same question 2. Second part says, is it possible to have an element with the quantum number n equal to 4? Okay, sorry, n equal to 3, I equal to 1, mx equals minus 1, and ml equals 0. Is it possible to have an element which have these quantum numbers? Okay, so to answer this, first of all, we define each of the quantum numbers and know if it is possible. So n is the principal quantum number. N stands for the principal quantum number. Okay, and the principal quantum number defines or tells us the main energy level to which an atom or an element belongs to. Okay, and it has values which ranges from n equal to 1, 2, 3, and so on. All right, so it tells us the main energy level to which an electron belongs to. That's the principal quantum number. So if we have n here to be equal to 3, and we know that the principal quantum number ranges from 1, 2, 3, and above, then it means it is true that an element can have n to be equal to 3. Now, second here is I. I signifies the azimuthal quantum number. So we have the azimuthal quantum number signified by I. The azimuthal quantum number relates the angular momentum of an element with its orbital, and it has values which ranges from 0. Okay, I ranges from has values from 0 to n minus 1. The azimuthal quantum number has values which ranges from 0 to n minus 1. So if we are given n to be equal to 3, it means n minus 1 becomes 3 minus 1, which is equal to 2. Hence, the azimuthal quantum number can simply be what? From 0 to 1 to 2, because we have n minus 1 here to be 2. So which means it is possible to have an element that has such an azimuthal quantum number of 1, of course. Let's consider now the third one. Third one says, okay, mx to be equal to minus 1. Now mx there stands for the spin quantum number. Okay, spin quantum number, and the spin quantum number denotes the spinning of the electrons around the orbit. And actually the spin quantum number has values ms only equal to minus 1 over 2 and plus 1 all over 2. So the spin quantum numbers have values only given as minus 1 over 2 and plus 1. These are the two values of the spin quantum number. But if you check in the combination, you're having the spin quantum number here to be equal to minus 1 Okay, we're having the spin quantum number to be equal to -1, which is not possible. Hence, it is not possible to have such a combination. Hence, it is not possible to have an element with n to be equal to 3, I to be equal to 1, mx to be equal to -1, and ml to be equal to 0. So there was no need to go about the magnetic quantum number, since at the spin quantum number it's already shown that it's not possible to have those combinations. So that becomes the answer. So these are the explanations you're going to give as your reasons. For the azimuthal quantum number, it holds. For the principal quantum number, it holds. But then the spin quantum number, of course, it cannot have. The only value for spin quantum number are -1/2 and +1/2. So saying -1 becomes what? Shows that it is not possible to have such. Alright, so the final question on still question 2 says list the possible quantum numbers when the principal quantum number is equal to 4. So you're asked to list the possible quantum number. This is the final question. When n is equal to 4. When the principal quantum number is equal to 4, you're asked to list the possible quantum number. So let's start with the azimuthal quantum number. So I said the azimuthal quantum number, okay, has values. Has values that ranges from 0 to n minus 1. So if n is equal to 4, then it means that n minus 1 becomes 4 minus 1, which is equal to 3. So which means each value ranges from 0 towards 3. Hence, I is equal to 0, 1, 2, and 3. That becomes the azimuthal quantum number when n is equal to 4. Let's talk about the magnetic quantum number. The magnetic quantum number actually depends on the values of the azimuthal quantum numbers. Okay, so when I is equal to 0, this is actually the s orbital. This is the s orbital. When I is equal to 0, ml is equal to 0. The magnetic quantum number is equal to 0. Now we have 0, 1, 2, 3 values for what? Azimuthal quantum number. So we have to find all the magnetic quantum number for the azimuthal quantum numbers. So when I is equal to 0, we have ml to be equal to 0. When the azimuthal quantum number I is equal to 1, this is now the p orbital. This is now the p orbital. Your ml value, the magnetic quantum number, actually ranges from -1 to 0 to +1. That is how it ranges. Okay, so if I is equal to 1, it means that the magnetic quantum number becomes -1, 0, and +1. This becomes your magnetic quantum number. When I is equal to 2, when I equals to, this is now the d orbital. Now we're going to have the magnetic quantum number ml to be equal to, starting from 2, it becomes now -2, -1, 0, +1, down to +2. Okay, and finally, when I is equal to 3, because we have 4 values of I from 0 to 3. So when I equals to 3, this is the f orbital. Okay, so we have the magnetic quantum number to be equal to, now you're starting from -3, it becomes -3, -2, -1, 0, 1, 2, and 3. So these are all the values of the magnetic quantum number. Finally, the spin quantum number. Okay, the spin quantum number, this one does not change. Spin quantum number ms remains -1 all over 2 and +1 all over 2. Alright guys, so that's the whole of that question answered. Okay, so I'll see you in the next video with the next question, question 3. Thanks and cheers.